Thank you very much, Krishna. Thank you for the introduction. Appreciate the introduction and the kind words. Do you see the screen, Krishna?
Yeah, I can see it. Put it in PowerPoint mode. Yeah, that's good. I can see it.
Thank you very much again, Krishna, for the introduction and the kind words. Thank you all for attending this seminar. I hope, as Krishna mentioned, we can all learn something from, the different sort of aspect of geoenvironmental engineering, specifically related to subsurface energy. So today I'm going to, briefly touch on a few technologies, specifically shale and geothermal and subsurface and CO2 sequestration. But first, I want to acknowledge, the many graduate and undergraduate students who worked over the years in the lab, and they have done, the hard work. The funding agencies have supported my research and enabled us to perform the research in these areas. The University of Vermont, in particular, our department, and many collaborators, as Krishna, alluded to over the years, whom I had the privilege to work with and collaborate. So I'll first briefly touch on the shale energy and some of the environmental impacts of the shale energy and some of the opportunities and the challenges that exist, specifically for us as geotechnical and geoenvironmental engineers. And then I'll briefly talk about the deep geothermal energy and the challenges, specifically the sustainability challenges, and also some of the environmental issues. And then later I'll talk about the CO2 sequestration technology and the associated issues, safety issues, environmental concerns and impacts, and finally I'll try to provide some general guidance and advice on the role of geotechnical and geoenvironmental engineers on these subsurface energy technologies. So if you look at the global renewable energy generation, these are just estimates, but you can get a sense that currently, at the end of 2019, about 72.7% of the generated electricity is from the non-renewable sources. And only around 27% of the generated electricity is from the renewable sources. So these are global numbers, of course, in different parts of the world, but these numbers will change. But what it tells you is that there is still a lot of gap between the renewable and the fossil fuels in particular. Out of the 27% of renewable, around 16% is the contribution of hydropower, around 6% from wind, 2.8% from solar. And then you'll see that the geothermal that I'm going to briefly touch on today has very small share, around 0.4% globally out of the renewable energy. So there is a lot of potential for geothermal to contribute more in the future to the advancement of the sustainable and greener energy. Now, if you put this in perspective in terms of world population increase, so currently the population of the world is around 8 billion, and the trajectory is that by end of the century, the population will be around 11 billion people. So we have to think about all different sources of renewable energy and sort of fill the gap between the transition away from the fossil fuels toward renewable. But the reality is that in different parts of the world, in different countries, there is still that large gap. But as geotechnical and geoenvironmental engineering, when we think about the sustainability, so we have to come up with some creative ways, some of the new ideas, and to push for more renewables in the future. Now, if you look specifically for the energy outlook in the United States, you can see that currently 2019 or 2020, around 37% of the energy generation is coming from natural gas. Most of it is basically from shale gas. Around 19% is the contribution of renewables, around 19% nuclear, and 24% coal. And if you look at the trajectory by 2050, you'll see that natural gas still plays an important role, more than 1/3 of the total generated energy, and the renewables is around 38%. Nuclear and coal are, sort of declining, which is good. So what I wanted to emphasize here is that still here in the United States, the renewable share by 2050 is far below what would be desired, and also the fact that natural gas still would contribute significantly to the energy generation here in the US. Now, if we break down the contribution of different renewable sources, you will see that solar and wind, they have the majority of the contribution to the renewables. And then if you look at the geothermal, you'll see that geothermal has very small contribution here in the United States, around 2%. And so the trajectory is that by 2050 still would be at that relatively very low percentage. So we think that there's still a lot of room for improvement for geothermal as a renewable compared to other sources of renewable energy. So in the first part of this talk, I'm going to briefly talk about the shale energy and some of the environmental impacts that the shale energy has, and some of the challenges, existing challenges, and some of the opportunities for us as geoenvironmental engineers to get involved and to improve at least some of the aspects of the shale energy, because it's still going to continue a major role in the United States, particularly for energy generation. The numbers that I'll provide here in this presentation, this talk related to shale, is mostly related to Marcellus Shale. And so Marcellus Shale, for those of you who are not familiar with, is basically a shale formation, a black dark shale formation, mostly in the northeast of the United States, covering almost 5 states, New York, Pennsylvania, West Virginia, parts of Ohio, and also the Maryland. So I guess most of you are familiar with the process of hydraulic fracturing. It's a controversial process. As you can see here in the schematic, the process typically starts with drilling the vertical portion of the well, and then once close to the shale formation, the horizontal drilling will start. So typically there are multiple lateral horizontal wells, and the shale formation will be fractured because of its extreme low permeability, so that the natural gas can be extracted from the wells. In Marcellus specifically, the vertical wells typically range between 3,000 to 8,000 feet. And a typical length for a horizontal well is around 4,000 feet, although it varies depending on the location. Typically on a pad, there are 1 or 2 vertical wells, and there are multiple horizontal wells to sort of minimize the environmental footprint at the surface. If you look at a typical shale gas well, you can see the well pad here at the top, and then the top portion of the well, which has the well casing, the horizontal portion of the well, and the lateral portion of the well multi-stage hydraulic fracturing is done in different stages. Once the stage is completed, then the other lateral portions of the well will be fractured. So this will be done incrementally to fracture the shale formation. If you look at the casing itself, the design of the well casing has changed over the years to sort of improve it, but you can see that there is significant risk posed to the groundwater contamination. For the scale, you can see the Liberty statue here. So although different portions of the well, at least the top portions of the well, are well protected using the casing, but there's still significant risk of leakage, and so I'll touch on that in a few slides. So this is again has improved over the years as the industry safety and has improved, but there is still significant risk for groundwater contamination, despite the fact that the well casing design and performance and also the construction process has improved in the field. Now, I mentioned that typically in Marcellus you have multiple wells on a pad. So here you can see in the schematic that typically there is one or two, three vertical wells, and then each of those have multiple lateral wells. So this is designed basically to minimize the footprint at the surface. But if you look at, well, I'll show you in a few slides that despite that idea of having multiple wells on a pad, there's still significant, footprint on the environment. So, as you're aware, there are many concerns associated with hydraulic fracturing and also shale energy, specifically shale gas extraction in general. But I'm going to touch on few of them. Not that it means that there are not other concerns, but these are some of the ones that are that we have looked at, and so they're more basically pronounced. So concerns with hydraulic fracturing itself, in particular, the water usage, the considerable amount of water that is being used for the process, some of the chemicals that are used in the process of fracturing, and what would happen to those injected fluids, what is the fate of those injected fluids, the water disposal, the flowback, which is basically the extracted fluid out of the ground, and then what are different treatment process, how it can be recycled and reused. Induced seismicity is another issue that is associated with fracturing. Other concerns include spills and leaks, obviously associated with any technology for extraction, and then groundwater contamination that I briefly touched, erosion and sedimentation, and NORM stands for normally occurring radioactive material, and T-norm that exists in the drilling cuts. So let's look at the water usage. These are just numbers for a typical Marcellus shale well in Pennsylvania. So you can see that a typical well uses about 4.5 million gallons per well, so about 68% of that water is coming from the surface water, 32% of that from water supply. So if we break down the numbers more, about 12% of that water is coming from the recycled. Now, once injected into a well in Marcellus, between 5 to 15% of that injected water will come back basically at the surface, which is called the flowback. So you can imagine that the flowback water contains significant amount of minerals, and in Marcellus in particular, NORM and T-norm. So there are many concerns on how to deal with the flowback water. So each pound that is used to basically hold water in a well pad during hydraulic fracturing process, each pound roughly contains 5 million gallons of water. A lot of remote areas in different parts of Marcellus, which translate into basically almost 1,000 trucks of water. So you can imagine a lot of truck shipment. Now, some of the chemicals that are used in hydraulic fracturing process, if you look at the pie chart here, about 90% of the injected fluid is water, and the rest, around 10%, is that propant. So propant is the material that will help keep the fractures open. And oftentimes sand is used as the propant. So about like 10% of the total composition is sand. And about 0.3% of that injected fluid is chemical. So there are different chemicals that are used for different purposes, including the scale inhibitor, corrosion control, and some of those chemicals will basically facilitate placement of propans inside the well. Now, in first look, it appears that 0.3% is not too much, but if you consider about 4.5 million gallons of fluid that is injected into each well, it's more than 10,000 gallons of chemical that is basically injected in each well. So there's considerable amount of chemicals that are injected in each well. Now, I mentioned the flowback. That basically is between 5 to 15% of the injected fluid that returns to the surface and needs to be either recycled and treated. So that poses a significant challenge. One of the issues with the flowback water is the high TDS level. And of course, in Marcellus, because of the radioactive material, so it also contains some, above the background level radioactive material or norm and tenol. So there are a lot of efforts to sort of recycle, and majority of the flowback is recycled currently in Marcellus. But there are also techniques to sort of pre-treatment the flowback, and some of the existing technologies or options for pre-treatment of the flowback is including the on-site treatment, the electrodialysis, crystallization, and other options for recycling of the wastewater. One of the sort of new proposed techniques is using CO2 as fracturing fluid, so that means that less recycling would be needed and less environmental impacts. And now in our lab, we tried electrodialysis as a sort of pre-treatment technique because of to sort of bring down the TDS level of flowback. So what you can see here on the left is basically the small device that one of my PhD students worked on. So she tried to use the principles of electrodialysis in order to lower the TDS level of the flowback, which was provided from Marcellus shale. So there are basically 5 chambers for the diluted and the concentrated flowback material. And here on the chart, I'll briefly show how basically it worked. So you can see the current on the x-axis and the change in the TDS level. These are for a 7-hour test period when we applied a low DC current. And you can see in all cases, the TDS level dropped by somewhere between 3 to almost 26%. So we tried different variables, including the time duration, which was the more sensitive parameter. Basically, the more you apply the current, the more you can bring down the TDS level. But also, you have to do a cost analysis to ensure that this is something feasible. So this was some sort of proof of concept that we tried in the lab to see if we can use electrodialysis as a pre-treatment approach to lower the TDS level of the flowback. As you can imagine, there's a significant risk associated with spills and leaks. So here in the images, you can see that typically on a well pad, there is 2 pounds, the water supply for the hydraulic fracturing, and another pound for storing the drill cuttings. Now, most of the water is being shipped by trucks. So because of the sort of stricter state and federal regulations, nowadays, typically the contractors use liners and liner beams to avoid spills and leaks. Typically all the water and the flowback is stored in containers, but there is still significant risk with spills and leaks. So typically in Pennsylvania, the flowback water is being, the portion of the flowback which is not recycled is being shipped to Ohio, and it will basically be stored using deep injection wells. So there's also risk of spills and leaks once the trucks are being shipped to the neighboring stage. Another area of concern with the shale is the gas leakage and groundwater contamination. So in Marcellus in particular, there are two formations above Marcellus. And so the vertical portion of the well basically penetrates through those two shale formations. And if the cementing job around the well casing is not done properly, as you can see here on the left of your screen, if there's poor zonal isolation, meaning that there's not good bonding between the cement and the casing, there will be methane leaks, basically, or gas leaks from these two formations above Marcellus, and which can basically go through the annals of the well and reach the groundwater and then contaminate the groundwater. So some of the initiatives that can sort of minimize or reduce that risk is doing, a good zonal isolation. And so the industry practice has improved over the years, and nowadays it's much better than what it was over like 20 years ago when it started in Texas and later in Marcellus, but still there's a lot of risk with groundwater contamination. And of course, no need to say the erosion and sedimentation that it causes to the environment. So you can see a typical well pad here, and the footprint of that. You can see the well ponds, and also on the right of your screen. So a typical well pad in Marcellus is between 3 to 8 acres. And then the transportation roads, the pipelines, these are all basically the stress that is caused to the environment because of the shale. Now, I mentioned earlier that using multiple wells on a single well pad, multiple lateral wells, it reduces the environmental footprint, but still you can see in that aerial photo that even doing that, you can see a significant disruption to the environment. Now, the other issue with shale is the drill cuttings that is coming out of the well during the fracturing process. So these drill cuttings, typically have radioactive material above the background level. That poses a significant challenge. Initially, like 20 years ago, they were simply being shipped to the landfill. But as the industry practices improved, now there is a specific practice for treating these drill cuttings. So there are different concerns associated with the drill cuttings. One being the radionuclides that leach from these cuttings, and they're exposed to rain once they're basically stored on the field. And then also the flowback, which was the other portion of the story here, is that it also contains a lot of radionuclides above the background level, which again needs specific attention and disposal. Now, the other risk is induced seismicity. So a lot of you are aware with induced seismicity associated with geoenergy technologies. For shale, although the risk of induced seismicity during fracturing stage is minimal compared to others, but majority of, or most of that risk is basically when the flowback is being shipped and wanted to be basically injected underground through disposal wells. So a lot of cases has occurred globally, here in the United States specifically, in Ohio, Youngstown, for example, in 2011, an earthquake above magnitude 4, which caused directly by injection of the waste fluid, specifically from Marcellus, and causing that damage in Ohio. So this is again another side of the story of flowback. Now, we've done some testing in the lab, some sort of geomechanical characterization of shale. specimens that were coming from different portions of the Marcellus. So there were some shallow cores around 450 and some deep cores from wells around 7,400 feet. In our lab, we have this Traxel equipment auto lab, which allows us to apply or to study the response of different rock, where there's flow or there's not flow, and can simulate the response of the rock specimens under in situ conditions in terms of pressure and temperature. So it's similar to a typical Traxel setup where you subject the specimens to confining pressure and axial pressure, and there's also core pressure, but with higher pressures so that you can study its relevant conditions in the lab. These are images of how you can set up the specimen and how you can wrap the piping to simulate the higher temperatures that you can see. For Marcellus shale, I'm just here providing this example in terms of the strength, specifically multi-stage failure, and how you can see this sedimentary rock when subjected to failure, how the strength will change. It's important from geomechanical perspective because you get the parameters that later you will need for the models that you want to develop, and you want to make sure that the extent and the direction of the fractures that will be created in the field. So on the right of your screen, you can see the CT images of this fractured specimens, the direction of the potential failure line, and how this brittle shale formation can respond to fracturing. Now, let's move on to the second portion of the presentation, which is on deep geothermal. I apologize, Krishna and others, for the noise my little sound is making. Sorry about that. So,
that's fine. Don't worry.
As I mentioned, it has great potential to increase the contribution of geothermal to the renewable energy. So the concept of deep geothermal is basically drilling a well to reach a high temperature bedrock. And this is a dry bedrock, and then drill a bunch of production wells surrounding that injection well. So now we can inject cold water, and that cold water will interact with that hot bedrock, and then the hot water, or in some cases the steam, is being injected and is being used in the power plant to generate electricity. In most cases, there are natural fractures within the bedrock, but there are also cases where this crystalline rock, including granite, you would need to create some new fractures. So that means that although the process is different, which is called hydroshearing than hydraulic fracturing, but some of the concerns that I referred to for shale, they also exist here for deep geothermal energy. So you can see here on the right of your screen a typical schematic of the geothermal energy in terms of temperature. Typically, the bedrock is somewhere between 150 to 200 degrees Celsius. A typical crystalline bedrock, a fractured granite reservoir, where the cold water is injected and being basically recirculated from the production well in the power plant, and the electricity will be generated. In terms of depth, different parts of the world, when we look at deep geothermal system, or enhanced geothermal, or EGS for short, typically it's above 3 kilometers, so 3 to 4 kilometers when you can reach that hot, dry bedrock. There have been many sort of trials and also some commercially operating EGS around the world, including here in the United States, in France, Australia, Germany, UK, and Switzerland. Some of them were successful proof of concepts, some of them were not. For example, the one in Switzerland, it was associated with induced seismicity, so the wells were shut off and the work did not continue. But some of the EGS are commercially operating currently in Australia, for example. Now, as you can imagine, when you inject fluid in the reservoir, in the EGS reservoir, now we're dealing with a coupled thermal, hydrological, mechanical, and chemical processes. So these processes are sort of linked, interlinked, and the link between different processes, between hydrological, thermal, mechanical, and chemical, are stronger in some senses, and in some areas they're weaker. But it's important to, the point of this schematic is to show that all of these processes are interconnected. So it's, you cannot sort of separate one and just study the hydrological or just study the chemical or thermal. So you have to look at it holistically. And so that's one of the challenges of studying, the response of an EGS, because it involves all of these processes. So some of the concerns that, again, these are some of the concerns with EGS development, the initial capital investments. So that's one of the inhibitors that most of the investments are not eager currently to invest in deep geothermal systems. Induced seismicity during stimulation. So most of the tremors are small in terms of magnitude, but there have been cases with larger tremors, magnitude over 3. There have been cases in Switzerland, for example, that the magnitude of the earthquake was even above magnitude 5. Similar to shale, the water consumption is also a concern here. Usually the injected fluid is recycled, but some cases disposal also can pose significant challenges. But if you think of in terms of sustainability and how we can improve the sustainability of EGS as a renewable source, over time, typically there's production decline, and that's because the existing fracture, natural fractures, and the created fractures over time will close under existing in situ stresses. And so closure of fracture will mean that less interaction between the injected fluid and the existing rock, and that means that less heat mining. So this is one of the major issues in terms of production decline in EGS that needs to be addressed. So as I mentioned, the process of creating fracture is a little bit different than shale. Here on the schematic, you can see that these are the naturally existing fractures under the existing stresses. And typically water is injected with relatively high pressure to sort of open up that existing natural fractures. And then later, some of these natural fractures will stay open, some of them will close. But in most EGS reservoirs, you also need to create new fractures to create pathways for the fluid to interact with the heat. On the schematic to the right, you can see that how an existing fracture will close over time. So under in situ stresses, you can see that mineral dissolution and precipitation is one of the main mechanisms that will lead to closure of fractures. So as the fluid interacts with the hot rock, it will sort of dissolve some of the minerals and precipitates along the way. So this mineral precipitation is one of the key contributing mechanisms to closure of fracture, aside from the closure under overburden stress, and also other mechanisms, including the pressure solution. So in our lab, we try to study how this mineral precipitation and dissolution will contribute to the closure of fracture. So two of the geothermal power plants in the west United States, including Blue Mountain and Patua. So we had rock specimens from these wells, which we prepared some specimens, fractured and natural specimens, some granite rocky specimens, which also, again, we prepared different specimens to study how the fluid will flow and the mineral precipitation dissolution and mechanical response of these specimens under reservoir conditions. Typical prepared specimens in the lab. You can see a jacketed specimen with the strain gauges. And so this was an example of fractured reservoir rock, and to see how the fluid will flow. You can see that the ultrasonic seismic velocities can be also measured through the crystals embedded at the top and at the bottom. So later in the slides, I'll show you a few examples of how it looks like basically when you start injecting the flow under high temperature and high pressure, similar conditions to the field. So here's an example of how the permeability will change and fracture aperture over time. So these are the data for two different tests, one of them under effective stress of 25, the other one under 35. So you can see that over time, the permeability of that fracture is slowly decreasing, again, because of the coupled processes involved, one of which is mineral precipitation and dissolution. So we can estimate using the Darcy law, the permeability of the rock specimens, and using the cubic law, we can estimate how the fracture aperture change. And later you can use, the CT images of pre and post test. You can compare them, and you can see how the fracture has been closed gradually over time. You can also look at the asperity opening over time and how it is evolving. You can see that the fracture has been gradually closing when you compare pre and post test. And you can also do the chemical analysis. Typically, we do the ICP analysis to figure out what is the change in the concentration of the minerals and the elements, which elements have been dissolved, which has been precipitated. And that basically allows us to better understand the flow response of these rock under the in situ stresses. The other work that we've done in the lab is basically to look at the change in the asperities, because these asperities can prop the fracture open and allow it to be open for the fluid to flow, and how it will change over time. Basically, it will provide a sense of how the fracture will close. And so remember, fracture closure is an important aspect of the work. And if we can keep the fracture open over time, that will improve the sustainability of the reservoir. Now, in the lab, we can also simulate the hydroshearing process. You can see this the rock specimen that has been the holes that have been drilled as injection and production wells, and then the sample is jacketed and mounted in the auto lab. So we try to simulate the hydroshearing process is involved in EGS in the lab, and study how that process will affect the permeability over time, and also how does it impact the fluid flow, as well as the stability, because one of the major concerns is the seismicity. So the friction of the two blocks will trigger the seismicity if it goes beyond the percentage of the shear strength. Later we looked at some of the precipitated minerals along the two edges of the block. So you can see on the right of your screen the precipitated minerals on the two ends of the fracture. And that was additional evidence of fracture precipitation along the edges of the fracture surface. And so it provided us with some insight into the precipitated minerals in the process of injecting the fluid in a similar condition to an EGS. Let me move on to the third part of the talk, which is related to CO2 sequestration or deep geological storage of CO2. So this is one of the technologies that can sort of alleviate some of the CO2 emissions. So the CO2 is typically captured at stationary sources and being transferred to the field and being injected under supercritical condition into the ground. So there are different candidates in terms of reservoir, but usually saline reservoirs are one of the ones that are often used currently. So this is relatively a new technology, but similar to the shale and also EGS or deep geothermal system that I mentioned. There's still a lot of unknowns and a lot of areas that needs specific attention because of the significant risk that it poses to the environment. So in terms of trapping mechanism, when this CO2 is being injected underground as a supercritical fluid, there are different trapping mechanisms that will help sort of keep the CO2 underground. These include the structural trapping, which is typically a low permeability cap rock. This is one of the conditions that the candidate side should possess. So the cap rock, because of the low perm, will not allow the injected CO2 to basically flow upward. The residual trapping is another mechanism. Basically, the CO2 will be trapped between the minerals. So as you can see here on the schematic, these are the grain scale, and the CO2 will be trapped. Solubility trapping, another mechanism that will contribute to trapping of CO2 in the reservoir, and the mineral trapping would be glass. So these trapping mechanisms will act in different time scales, and so some of them contribute initially and more compared to others, but over time, specifically hundreds and thousands of years, the other trapping mechanism will start to contribute more and more. So it's also important to keep in mind that this is our current understanding of how the supercritical CO2 will interact with the reservoir rock, and how this trapping mechanism will contribute toward sort of safe storage of CO2. But there are, again, as I mentioned, many unknowns that needs to be looked at more carefully and addressed in future. So some of the major safety issues and uncertainties associated with deep geological storage of CO2 is sort of summarized here in the slide. So here's an injection well where the CO2 in terms of supercritical will be injected and will be stored underground. So there are many abundant oil and gas wells. So if one of those are in the neighborhood of the injected CO2, then there's risk of CO2 leakage. But there's also risk of contaminating the groundwater and some of the neighboring reservoirs. So in general, the reservoir integrity is a concern. So if there is fracture in the cap rock, there is always a concern that the CO2 will leak up and also will compromise the integrity of the reservoir. The wellbore stability, as in many other technologies, is another issue. Here, of course, is more concerning in the sense that the CO2 may leak and may contaminate the groundwater as well as the atmosphere. Similar to other technologies, induced seismicity is another concern. So if you have existing fractures and close by faults, if we go above the injection pressure, that may trigger the seismic event in the site, and there have been a few cases of induced seismicity, although very minor, but this is still a concern associated with CO2 injection. And then leakage, as I mentioned, so there are many areas that potentially CO2 can leak and then contaminate the groundwater and the surface. So these are some of the major safety and uncertainty issues. And of course, all of these are caused by variation of pore regime, transport properties, the stress regime, as well as the mechanical properties of the host rock. If we specifically look at the larger scale leakage and the concerns, so that typically can result in human and livestock deaths. It could also contaminate the groundwater. There have been cases of groundwater contamination. And of course, it also affects the ecosystem, underground ecosystem, because of the higher CO2 concentration and the pH reduction. So these are some of the main, concerns with the potential larger scale CO2 leakage. Now in the lab, we have tried to, study the response of CO2 injection into deep saline formations using rock specimens that resemble those formations. And what you can see here in the plots, so these are basically the CO2 enriched brine injected into sandstone specimens in different stages over time. And you can see how the permeability of that sandstone specimen is increasing over time because of the injection of CO2. And the other specimens that we had with different mineralogy to investigate the effect of mineralogy on the response of the specimens. And then, of course, you can look at the weakening of the specimens, how the Young's modulus has changed, and you can see a drastic sort of weakening of the rock specimen in both cases that has occurred. So I'll try to be quick so that I can get to some of the questions that you might have. We also looked at the ultrasonic wave velocities. On the left, you can see the stress path as an example, and how the wave velocities will change once you start injecting that CO2, which is another indication of weakening of the rock specimen, which can pose significant, safety issues and safety concerns in both the specimens. When you compare the intact and the injected specimens, you can see significant reduction in ultrasonic wave velocities. And of course, if you look at the fracture aperture and how the permeability evolves over time, you can see that the permeability is increasing over time for different specimens that we tried. In part contributed to the dissolution of the minerals because of the injection of CO2 and later the weakening of the rock. So in essence, we're changing the pore structure of that rock. So these were very sort of brief overview of the three technologies, including shale energy, geothermal energy, and CO2 sequestration. And as you saw and you heard, there are many areas of safety concerns, environmental concerns, and so there is a lot of room for us as geoenvironmental and also geotechnical engineers to get involved. Some of these technologies, including hydraulic fracturing for shale, they're not going away, at least for the next few decades. The hope is that transition faster away from fossil fuels, but in different parts of the world, they're still going to exist. So our role as geoenvironmental engineers is to think about how we can improve it and how we can make it safer, or at least more environmental friendly. Deep geothermal, there's great potential, but also there are a lot of concerns that needs to be addressed. So similarly with the CO2 sequestration, there's some safety, there are uncertainty and safety issues, but technology is gaining more attention in recent years. So you can see that there's still a lot of room for research to answer some of these unknown questions, and hopefully trying to improve these technologies. And as a whole, we try to push for more renewable energy and getting away from this fossil fuels. So thank you very much for your time. I would be happy to answer questions.